All right, now let's come back and continue. So let's start. Let's look at the stacking framework. So the project two will follow the exactly the same framework, and I have to point out that if you search stacking on the internet, most likely you won't find a correct version. So far, all the existing version on the internet, except the original paper, are not correct. They have errors here and there, but our framework exactly follows the stacking model that proposed in the original paper. That is a paper in 1922, and so this lecture, this 1 hour, is extremely important for you to finish project 2. So just make sure that you have understand each and every step, and make sure during your project 2 you have followed the slides and the lecture when you implement a stacking method. All right. So the stacking framework, there are two phases. One is training and one is testing. So for the training, the first step is to prepare training data for base models. And the step 2 is to learn the base classifiers. As you will see, there are multiple base classifiers that need to be learned. And the third step is that after we have learned the base classifier, we need to generate features or meta features for meta model. And the fourth step would be learn a meta classifier. And for the testing, the fifth step would be generate features for meta classifier based on the result of the base classifiers, or the prediction result of the base classifiers. And the sixth step would be prediction using meta classifier. Now let's start from the first step, and let's dive into the details of each and every steps here. So the first step would be prepare a training data for base models. Here, in terms of base models, again, you should distinguish the definition between models and classifiers. So classifiers is like a specific instance of a model. Right? A model is a more general concept. And in terms of base classifiers, we need two types of base classifiers, where the first type is to offer the meta feature for the when we do the training, or for train the meta classifier. And the second type would be offer the meta features when testing or do the prediction. So why we need two different types of base classifiers? It is because let's look at the first type of base classifiers first. Here we propose to use the k-fold, the idea similar to the k-fold cross-validation. So basically we split the training data into k groups, and in each iteration we use k-1 groups to train a base classifier, and the left one is used to obtain the prediction and generate the meta features. And this procedure will be repeated k times. All right, and all right. So the question would be, what if we train these base classifiers as a whole? Right. The problem is that it will cause an overfitting, right? Because well, it is also related to the second type, but we will left that for later. So here, if we train the base classifiers as a whole, then the training data would act like the training input of the base classifiers, but the base classifiers will generate the prediction of the base classifiers, which is meaningless, and also the prediction will be used to train to form the meta feature and train the meta classifier, but still on this on this training data. So there will be a huge overfitting under these circumstances. And also, I mean, for the type 2, we train as a whole. This is to generate the meta features for the prediction or for the testing. But if we use the same classifier as trained in the first stage, right? Because of this overfitting, it will hugely affect the performance of this meta classifier, or the performance or the prediction accuracy. So that's why we need two types of base classifiers, and we apply different strategy when we train these base classifiers. And remember, the purpose of this base classifier is to generate meta features in order to train the meta classifier. All right. Now let's look at a concrete example to see how do we prepare the training data for base models. Right. So as the first stage, step, this is the raw data frame, which, as you can see, we only have text, sentences, and category. Here in this project, we have these three different categories. They correspond to food is so this text are reviews, online reviews, and food means that the reviews are involving the comments on food. And the PAS, it means that the reviews involves comments on the price of the food, the ambience of the food, and the service of the restaurant. This is PAS stands for. And MISC is that for those reviews that does not belong to any of these two categories, or the reviews that actually are a mixture of PAS or food. Right. All right, so these are three different categories, and these are the text, and they form the raw data frame. We have raw data, and we have the category. So the first thing to do, actually you can switch the order of these two, it doesn't matter, but let's first partition the data into k different groups. So in order to achieve that, we assign a random integer to each and every row. So these are 1, 4, 2. They are random integers. And in this project, we let k equals to 5. So this random integers is in 1 to 5. Right? So the first stage is to randomly partition them into k groups. So for short, we just assign a group ID to each and every row, and the group ID is a random generated integer. And the second step is to generate features and labels. So in order to generate labels, as we have shown before, you can use a string indexer to convert the categories into labels. So basically, MISC is converted into 0, and PAS is converted into 1, and food is converted into 2. So we have 3 categories, so 3 types of labels. So it is a multi-label classification problem. Right? And in order to generate the features, here in this project, we just use the word count as the features of each and every sentence. So it is extremely easy. In order to generate features, you need to do tokenization first, and then do the count vectorizer. Right. Then you kind of generate the features. So after all this, we convert text to feature vectors. We convert category to labels, and we add a randomly integer as a group ID to each and every row. All right. Note that because it is a multi-label classification problem, but this slide should be in before, but basically we have 3 labels, 3 label types. So it's a multi-label classification problem. But some model can only handle binary classification problem, for example, the SVM. All right. So in order to handle this issue, we will instead build say one versus rest classifiers. Right. So this say is the number of label types in the data set. So in our case, the size of say equals to 3. Right. So this one versus rest classifiers means that each classifier predicts whether the sample is class Ci or not. Then in step 1, when we prepare the training data for base models, we need to also convert this label to using this one versus rest. In order to support the one versus rest classification problems, we need to add 3 more labels corresponds to whether the label equals to 0 or not, whether the label equals to 1 or not, and whether the label equals to 2 or not. And as you can see, here 1 means true, right? 0 means false. And because the first row the label is 0, so label equals to 0 or not, it is true. Hence the 1 here. And for the rest 2 rows, the label does not equal to 0, so we assign 0 here. And we can do the same thing for for label equals to 1 or not and label equals to 2 or not. We have label 0, label 1, and label 2 as the 3 new columns. So as a summarize, we this is the row data frame. We randomly partition them into k groups by assigning the random group ID, and generate features and the labels, and further divided the labels into 3 label columns, label 0, label 1, and label 2. So this one was used to train the base classifiers for training. This one was used to train the meta classifier, as you will see later. But this one will be used to do the prediction, right, or to train the base classifier that is used for prediction. All right, so for now, just remember how do we convert the original raw data frame into this the training data. All right, so basically we generate the feature columns, the label columns, and the label columns for the 1 versus rest classifiers. All right, so this these columns will, all of them will be used in the following steps. So here is how we because now we have the group IDs, and this here is how we use this. Say we use this group IDs to help us to form or to split data into different groups, and then to form train and prediction sets for different base classifiers. So basically, here's the data. With the group ID, we can split the data into 5 different groups. 5 different groups. And then we can generate 5 sets of training data and prediction data, let's say. So basically, for the first group, for the first set, we use first group as the data which we will generate predictions, and we use the rest to train a model. So in ice set, we use group I for prediction, and we use other groups for training. So as you can see here, all right. So we the group that is for prediction is exactly the group I. So 1, 2, 3, 4, 5 here, and the rest are used to train base classifiers. So basically, we would have 5 different sets. And each of them would be used to train a set of not one, but a set of base classifiers, and this one would be used to generate the prediction of that base classifier, and the prediction will be used to form the meta features that is used to train the meta classifier. Well, it sounds pretty complicated, but no worries. We will show you how this whole thing goes through. Right, so no worries. And also remember the data here, data used in this step is the data here. So we need features, we need label 1, 2, 3, and we need group only to form different groups. All right, so that is the first step. And now let's look at the second step. We have already mentioned here. So basically the second step is to learn the base classifiers. And as we have mentioned before in these slides, because we're dealing with a multi-label classification problem, and some models can only handle binary classification problem. So we use this one versus rest trick to use let's say for example SVM to do this multi-label classification problem. And as you can see, I mean the input label would be whether it belongs to type I or not, and also the prediction would be the same. I mean whether it belongs to type I or not. And as you can see, because we actually convert it into three different. Yeah, we convert it into three different classifiers. All right, so we need to train this much classifiers. So in project 2, we use naive Bayes and SVM as base models, and we know that the number of label types is 3. Then how many classifiers do we need to train? Now we know that we have 5 groups. We have 5 groups. And for each group, we need to, for each group, we have 3 labels, label 1, 2, label 0, 1, and 2. 3 labels. And for each label, we need to train a classifier for naive Bayes and a classifier for SVM. So it's 2 classifiers. So this part, we would have 30 classifiers to train. Note that naive Bayes actually can handle a multi-label classification problem, but in order to reduce the difficulty of this project, we also use one versus rest on naive Bayes classifier. All right, so both naive Bayes and SVM, we need to train a classifier on the 3 different labels. And this is the first type base classifiers. If you still remember, we have mentioned here, right? These are the one that offer the meta features when training, and we also need base classifiers to offer the meta features when testing. Right? And these classifiers they were trained on the whole training data set. So it would be this. Sorry, here I actually made a mistake. Made a mistake here. Both base classifier. These are wrong. All the base classifiers will be trained on this on this kind of training data, and the meta classifier will be trained using the labels here, but here, not the features here, but the meta features, which you will see later. All right, so that is just an error to correct. Back to here, the second type of the base classifier, which is trained on the whole data set. So here would be 1, but still it has 3 labels and has 2 classifiers. So it comes to 6 classifiers. So in total, we would have 36 base classifiers to train. Now let's look at exactly what should we use as the training data when we train these different classifiers, base classifiers. Now this is, as you can see, this is the example here is group 3, right? Or the set, the third set, or the third set. That's why we have group 3 is for prediction, and we have group 1, 2, 4, 5. They form a training data, and we firstly train the base classifiers with label 0, because with label 0 we kind of train the classifier to classify whether the label is 0 or not. Right. So in order to do that, with this training data with label 0, we need to train 2 classifiers, which are naive Bayes and SVM. So the 0 here is the label, corresponds to the label, and the 3 here corresponds to the third iteration, or the third set. And we do the same, as you can see, we do the same for training data with label 1, training data with label 2. Here as the input for these classifiers is label 0 and features that we have generated. So label 0 and features will be given as the input of all these classifiers. So the above procedure will be repeated k times. It means we would have, say, MB classifier IJ and SVM classifier IJ, where I is from 0 to 2, J is from 1 to 5. All right. So you need all these different base classifiers. And we also need to train the base classifiers for the projection. For the testing phase, or for the prediction phase. In that case, we use the whole data set with features and label 0, 1, 2 as the input. And similarly, we train the data with label 0, train the data with label 1, and train the data with label 2. We will generate the naive Bayes classifiers and SVM classifiers. But since there is we don't split the data into groups, so we only generate classifier 0, 1, and 2. That is corresponds to label 0, 1, and 2. Right. And of course, this step we'll only do once. There's nothing to repeat. So step 2, just that's all for step 2. Just remember we need to build or learn base classifiers for 2 types of different base classifiers, and this is the first type, and these are the first type, and these are for the second type, and just to make sure that you have learned all of them. And the third step would be how do we generate features or meta features for meta model based on the base classifiers. So as we have, if you still remember, as we have mentioned before, the meta features would be based on the prediction results from each base classifier. And you can also use additional meta features to improve the performance of the classifier. So in this project, we consider 2 types of meta features. One is the prediction result from each classifier, and the other is the joint prediction result from all the base classifiers, or more specifically from base classifiers with the same label systems, or they essentially predict the same thing, whether it is belongs to table I or not. So for the single projection result from each base classifier, we would generate C times 2 features, because this C is the different, say, the number of labels, and this 2 is the naive Bayes and SVM. So you can imagine we would have 6 features in total. And for the joint prediction results, we consider them from the prediction result from classifiers with same label system. So in this case, we kind of concatenate the prediction result from naive Bayes classifier and SVM classifier to form a new meta feature. All right, so then we in this case we will generate 3 meta features, right? And actually for all the meta features, for each of the meta features, we will use a one-hot encoder, not only for a joint prediction result. Let me correct this. So basically, all of them are one-hot encoded. All right, still let's look at the example here, which would be much easier to understand. So we still take group 3 as the example, but you can imagine we will do the same thing for group 1, 2, 3, 4, 5, 5 of them. So we predict data. We predict data with label 0, with label 1, with label 2. So in this case, the input is group 3, the features in group 3. Will be the input to each and every classifiers. Right. So here again, this is for label 0, for label 1 and label 2. These are the classifiers for group 3. All right. So for each row, we would have a prediction. Here 0 means it does not belong to the label 0, and 1 means the classifier, since it is more likely to be label 0, and so on and so forth. So we have 6 base classifiers here, and each of them will give their own prediction. So the single prediction would be 6, either 0 or 1. And we do the one-hot encoding. One-hot encoding means because we have only 2 of possible results, either 0 or 1. So for one-hot encoding, it will use 2 bits or 2 real numbers or integers. Actually, should be integers, but stored as real numbers. So here is this bit is equals to 0, and here is equals to 1. Right. So 1 means true and 0 means false. Right. So by using one-hot encoding, 0 becomes a vector of 0, 1, which means it is true that it equals to 0, and it is false that it equals to 1. And for the similar reason, 1 is converted into 1, 0, and 0 is converted into 0, 1. They're all the same. I need to point out here that in the real program or the data frame, the one-hot encoded vector may not look like this. Spark machine learning library tends to use sparse vector to store these one-hot encoded feature vectors. So you might see different, slightly different representation of these one-hot encoded vectors, but essentially they are the same. Right. Here, just for you to understand the whole procedure, we use the dense vector to represent this. Right. So this is for step 3. This is for the single prediction. The single prediction meta features. And for the joint prediction meta features, as we said, we joint the predictions from the same label system. Right. So, so still, I mean, there's no need to do the prediction again. We can just take the single predictions as here, but we combine 2 of them from the same label system to form a joint prediction. So we have 0, 1, 1, 1, and 1, 0 here. And as you can imagine, all the possible joint prediction would be 0, 0, 0, 1, 1, 0, and 1, 1. Right? So 4 of them, 4 different possibilities. So if we do the one-hot encoding, we would have a vector of 4, where just one of them is 1, indicates the one that the joint prediction is, and the others are 0. So basically, this should be 1, 1. This should be 1, 0, 0, 1, and 0, 0. So 0 and 1 are essentially an indicator. All right. And these are the one-hot encoded feature vectors that you have got. And for the meta feature, for the final meta feature, we just concatenate all these things together. So we have 0, 1, 1, 0, and so on and so forth, 6 of them, which are the 6 of them here. we have this 0, 0, 1, 0 from this red part, this green part, and the purple part. So now for each group with these classifiers, we can generate, for each row, we can generate a meta feature, right? So if you still remember, or if you understand correctly, you would be able to see that here we generate the meta features for data in group 1, and here we generate meta features for data in group 2, and so on and so forth. Then if we union them together, we would have the meta features for all the data, right? Because for any row in the original data frame, it belongs to one of the group, 1 or 2 or 3 or 4 or 5, and according to its group, we are able to obtain the meta features, right? So the meta features comes from these base classifiers, and the group is what we have generated before, and the labels is what we have generated before. So this is step 3, how we generate features for meta model in order to train the meta feature. And some of you may ask, like, do we forgot those classifier 0, classifier 1, or classifier 2? Those classifiers will be used to generate meta features for prediction. So it is not in the first phase. We will do it later. All right. So step 4, we learn the meta classifier. So learning is really simple as long as we have this, right? So we use meta features as features. If you know what I mean, here when you build the pipeline, you need to specify the features column and the label column, right? So here we use meta features as features, right? So this is the feature column, right? And this is the label column. And then we can learn the meta classifier on the whole data set. Right. In project 2, we will use a logistic regression as the meta model. And logistic regression is a multi-class classifier. So we don't need to convert the labels into label 0, label 1, and label 2. We can just use the labels here, right, to build this meta classifier. And till now, we have built the meta classifier. Means we have finished the first phase, the training phase. And then it is time to do the prediction. All right. So step 5 is to generate meta features for prediction, because we have already learned the base classifiers for prediction. So we can generate the meta features. So in step 2, we have learned base classifiers for meta feature generation in testing phase. And before using meta classifiers to do the prediction, we need to generate meta features in a similar way as step 3. So just as you can see here, these are the features. these are the features of the testing data. And these features can be used as input to all these base classifiers. And each of them, for each row, will give a prediction. Right? So these are the single prediction, and these are the joint prediction. And we, again, do the one-hot encoding using the same pipeline, actually. Here you need to make sure that you're using the same pipeline. Or say if you're not using the pipeline, you need to fit on training data and transform in this step. All right. So in this case, you would have the meta features formed like this. I believe you all know how it comes from. And once we got the meta features, in the last step, we can do the prediction. So we do the prediction using meta classifier. So meta classifier is the classifier that has been trained before. All right. So we use the meta classifier that trained in step 4 to predict labels for the test data with meta features generated in step 5. So because it is the prediction phase, we only need the meta features as input of the meta classifier, and we will have the prediction. Then it's all done. All right. We can do evaluations if we like to see whether it has improved. It has improved the performance or not. So that's pretty much all for the stacking part. In terms of project 2, it will be released in this week. The whole teaching team work hardly on the project 2 because we are adjusting the difficulty based on the result of project 1. And to be honest, the result of project 1 is not good enough. It's worse than I expected. So we are trying to adjust the difficulty of project 2. The deadline would be the end of week 10 because this is the school policy. We can't have a due date after week 10, but the time is more than enough. I guarantee you the time is more than enough if you don't rush it in the last 3 days. So do it as early as possible. We will try to make it public as early as possible as well. So in order to do project 2, you are required to implement a stacking model. All right, so there are 3 labels, as you have already seen. We use SVM and naive Bayes as base models. We use logistic regression as meta model. All right, and you are required to use a data frame and pipeline to help you with the implementation. So it's I believe all the things that you need has been discussed in week 7 and week 8. All right, and there's no running time requirements. Of course, I mean your program shouldn't be too slow. So trying to avoid unnecessary operations, but we won't have we won't be like in project 1 we evaluate or we mark your submission based on the running time. Not this time. All right, the marking criteria will mainly based on the accuracy of your classifier, or the way you implement the stacking model, whether it is correct or not. All right, so that's pretty much all for today, and yeah, we will release project 2 and lab 3 on this week, and yeah, that's all. Thank you for watching, and see you on next Monday.